In the realm of missing data analysis, multiple imputation, MI, is a state-of-the-art method for handling missing values in datasets. The multivariate imputation by chained equations (MICE) approach, in particular, offers flexibility in accommodating various data measurement levels. However, it requires specifying a univariate imputation model for each variable under imputation, which can be challenging. This process involves deciding on the imputation model form and the predictors to include, with an emphasis on incorporating as much information as possible from the data to minimize bias and maximize efficiency. To simplify this process and enable the inclusion of more predictors than traditionally possible, high-dimensional prediction models have been integrated with MICE. These models include ridge regression, lasso regression, decision trees, and principal component analysis (PCA). Among these, PCA has shown promising results in summarizing a large set of predictors using a few independent linear combinations. A comparative study by Costantini et al. 2023 found that using PCA to create summaries of potential imputation model predictors performs well in terms of estimation bias and confidence interval coverage. In a follow-up study, Costantini et al. 2023 explored different ways of utilizing PCA with the MICE algorithm, concluding that updating the principal components for the imputation of every variable at every iteration provides the lowest bias and deviation from nominal confidence interval coverage. However, this approach relies heavily on the number of components computed, which is often unknown to researchers. To achieve small bias and satisfactory coverage, it is recommended to retain at least as many PCs as the number of latent variables in the data-generating model, which is undesirable due to the lack of knowledge about the true number of latent variables. PCA, as an unsupervised dimensionality reduction technique, summarizes the variability of a set of variables measured on observations with a set of cube principal components. This summary aims to preserve the essence of the original research paper, focusing on the challenges of specifying univariate imputation models in MICE, the integration of high-dimensional prediction models, and the promising results of using PCA. The study highlights the importance of updating principal components for each variable at every iteration and the need for further research to determine the optimal number of PCs to retain. The study explores the potential of using supervised dimensionality reduction (SDR) techniques in the multivariate imputation by chained equations (MICE) algorithm to improve upon unsupervised principal component regression (PCR). MICE is an iterative algorithm that imputes multivariate missing data on a variable-by-variable basis, using variable-specific conditional distributions. The algorithm starts with initial guesses for missing values and iteratively updates these imputations based on the fully conditional posterior distribution and the posterior predictive distribution. After convergence, the imputations are assumed to be samples from the target multivariate distribution, and analysis models are estimated on each imputed dataset, with parameter estimates pooled using Rubin's rules. The paper highlights the need for dimensionality reduction techniques, such as PCA, to specify imputation models in MICE, especially when dealing with large datasets. PCA finds a low-dimensional representation of variables in a data matrix, maximizing variance and minimizing information loss. However, PCA does not consider the dependent variable in its computation, which may result in PCs unrelated or weakly related to the dependent variable. The authors propose using SDR techniques within MICE to address this limitation. SDR techniques use the outcome variable to guide the computation, ensuring that the resulting PCs are both good representations of the predictor variables and strongly associated with the dependent variable. This could potentially relax the requirement of using at least as many PCs as the number of latent variables in the data-generating model, as suggested by Costantini, Lang, Sijtsma, and Reiskens, 2023. The study uses a Monte Carlo simulation to evaluate the performance of different versions of SDR with the MICE algorithm. The paper aims to answer two questions. First, what are the statistical properties, bias, coverage, confidence interval width, of parameters estimated from data treated with the MICE algorithm using different versions of SDR as the univariate imputation models? Second, can using SDR in MICE relax the PCA requirement of using at least as many PCs as the number of latent variables in the data generating model? Principal component analysis, PCA, is a dimensionality reduction technique that projects high-dimensional data onto a lower-dimensional subspace, retaining most of the original data's variability. The principal components, PCs, are the orthogonal directions of maximum variance in the data. The first PC explains the most variance, the second PC explains the maximum variance orthogonal to the first, and so on. In principal component regression, PCR, the PCs are used as predictors instead of the original variables. This approach is useful when dealing with high-dimensional data or highly correlated variables. The optimal number of PCs, Q, is typically much smaller than the original dimensionality. P cross-validation is often used to determine the best value of Q. Multiple imputation with principal component regression, MIPCR, incorporates PCR into the multiple imputation by chained equations, MICE, framework. At each iteration, PCs are extracted and used as predictors in the univariate imputation model. This approach allows for the inclusion of all predictors in the imputation model, bypassing model selection, while preserving the advantages of an inclusive strategy. However, MIPCR's performance is highly sensitive to the number of PCs computed, and performing PCA on large datasets can be computationally demanding. An alternative to PCA is supervised dimensionality reduction, SDR, which takes into account the relationship between the predictors and the outcome variable. SDR methods can compute PCs that are better predictors of the variables under imputation, potentially allowing for fewer PCs to be retained. 3 alternative approaches to finding linear combinations of the predictors are proposed, including supervised principal component regression, which computes PCs only on the subset of variables associated with the dependent variable. These approaches are then implemented as univariate imputation methods within the MICE algorithm. The presented research focuses on improving imputation methods in multiple imputation by chained equations, MICE, by incorporating supervised principal component regression, SPCR. SPCR enhances the predictive performance by selecting relevant variables for principal component computation. This approach, referred to as MISPCR, uses cross-validation to determine the optimal threshold for variable selection and the number of principal components. The method leverages the strength of associations between variables and the outcome to improve imputation accuracy. It differs from traditional principal component regression, PCR, by actively excluding uninteresting variables, making it more suitable for predictive tasks. The use of SPCR within MICE offers a novel solution for imputation, particularly in scenarios where the relationship between variables and the outcome is complex. The research highlights the importance of careful variable selection in imputation models and demonstrates how MISPCR can outperform traditional methods in terms of predictive performance. The proposed algorithm for imputation under the SPCR model with Bootstrap, as outlined in Algorithm 2, involves a series of steps that prioritize both the reconstruction of predictor variables and the dependent variable. This is achieved by minimizing a weighted combination of reconstruction errors for both x and y, subject to certain constraints. The value of alpha, which determines the emphasis on reconstructing x versus y, can be found through cross-validation or maximum likelihood principles. In the context of MICE, using PCOVR as a univariate imputation model, MIPCOVR, allows for continuous supervision, downweighting irrelevant variables but not excluding them entirely. In contrast, partial least square regression, PLSR, is a dimensionality reduction technique that seeks linear combinations that account for a large proportion of the variance in predictors and correlate strongly with the dependent variable. Unlike PCR, SPCR, and PCOVR, PLSR computes one linear combination at a time and stops at the required number of PLS components Q. The estimation of the first PLS component, T1, is based on computing the vector of weights W1, with elements W1, J equals exig for J element of 1, P, the inner products between each predictor xj and the dependent variable y. Here is the combined summary of pages 11 and 12. The paper presents several imputation methods under the multiple imputation by chained equations, MICE, framework. Algorithm 3 describes the imputation procedure under the partial covariance response regression (PCOVR) model with Bootstrap, which involves drawing a bootstrap version of the observed cases, centering and scaling the data, computing the value of alpha, estimating the partial covariance response matrix, and obtaining imputations by adding normally distributed errors scaled by the residual error variance. The paper also derives the constructed variable t1 and orthogonalizes x1 to xp with respect to t1. The partial least squares regression (PLSR) algorithm is used to obtain imputations, where the QTH weight vector maximizes the optimization criterion of squared correlation between the response variable and the linear combination of predictors, divided by the variance of the linear combination. Algorithm 4 describes the univariate imputation method based on PLSR, which involves drawing a bootstrap version of the observed cases, estimating PLSR with Q components, estimating the residual error variance, obtaining predicted values for the missing data, and adding noise scaled by the residual error variance to obtain imputations. The paper summarizes the differences between the univariate imputation models used within the mice algorithm, including MIPCR, MISPCR, MIPCOVR, and MIPLSR, in terms of supervision type, optimization criterion, estimated parameters, and tuning parameters. A simulation study is conducted to investigate the relative performance of unsupervised PCR and the supervised alternatives, including estimation bias, confidence interval width, and confidence interval coverage of several analysis model parameters obtained after imputation. The study varies the dimensionality of the latent structure, the proportion of missing values, the missing data mechanism, and the number of components used as predictors in the imputation models. The research paper discusses an experimental study on missing data imputation using multiple imputation methods. The study involves generating datasets based on a confirmatory factor analysis model, introducing missing values, and then imputing these missing values using different methods. The goal is to assess the performance of these imputation methods under various conditions. The data generation process involves a 1000 XP data matrix C, with P being the number of items measuring each latent variable. The factor loading matrix lambda is designed to represent a simple structure, common in social science surveys. The study considers different numbers of latent variables, L, as an experimental factor, with levels 2, 10, and 50. Missing data is generated on 3 items measuring the first latent variable, with proportions of missing values set at 0.1, 0.25, and 0.5. The missing data mechanism includes both missing completely at random, MCAR, and missing at random, MAR, scenarios. The imputation methods assessed include MIPCR, MISPCR, MIPCOVR, MIPLS, MIQP, MIAM, MIALL, CC, and FO. The study aims to understand how well supervision can overcome the limitations of MIPCR and to evaluate the performance of these imputation methods under different conditions. The research discusses the development of a novel missing data imputation method, focusing on dimensionality reduction techniques. The approach involves using logistic regression to model missingness and 4-dimension reduction-based methods for imputation. These methods include MIPCR, MISPCR, MIPCOVR, and MIPLSR, along with traditional approaches like MIALL and MIQP. The study also compares these methods using metrics such as absolute percent relative bias, PRB, average width of confidence intervals, CIW, and confidence interval coverage, CIC. The results highlight the effectiveness of the dimensionality reduction-based methods in reducing bias and improving statistical efficiency, while maintaining good confidence interval coverage. The research emphasizes the importance of selecting the optimal number of components in dimensionality reduction methods and provides insights into the performance of different imputation techniques under various conditions. The research paper discusses the application of supervised dimensionality reduction techniques in multiple imputation (MI) for missing data. It focuses on the correlation between 2 items with missing values, comparing different methods such as MIPCR, MISPCR, MIPCOVR, and MIPLSR. The study uses a data-generating model with varying numbers of latent variables and components retained by the methods. Results indicate that MIPCR requires the number of components to be greater or equal to the number of latent variables for acceptable bias and coverage. MISPCR performed better, especially with fewer components, while MIPCOVR and MIPLSR showed more stable bias performance. The paper also compares these results with traditional MI approaches and complete case analysis, highlighting the advantages of supervised dimensionality reduction techniques. The findings suggest that meeting the requirement of equal components and latent variables is not sufficient for good imputations, especially for a large number of latent variables. Here is the combined summary of pages 19 and 20. The authors investigate the performance of PCA-based imputation methods, specifically SDRBASED mice, in automatic imputation model specification. Figure 2 presents the confidence interval width, CIW, for the estimated correlation coefficient between the first two items imputed, as a function of the number of components used by the PCA-based imputation methods. The results show that SDRBASED methods, retaining just a few components, resulted in small bias and good confidence interval coverage, independent of the number of latent variables in the data-generating model. In contrast, MIPCR exhibited large bias and low coverage when using a small number of components. These findings suggest that SDRBASED mice is more appropriate than PCRBASED mice for automatic imputation model specification. Among the SDRBASED methods, MISPCR demonstrated superior statistical properties, with smaller bias and better coverage for a wider range of retained components compared to MIPCOVR and MIPLSR. Figure 3 illustrates the coverage intervals for the estimated correlation coefficient, highlighting that MISPCR achieved a smaller bias than MIPLSR when retaining fewer components and resulted in consistently closer to nominal coverages. The results imply that the discrete type of supervision employed by MISPCR should be preferred to the continuous type employed by MIPCOVR and MIPLSR in the context of imputation of data with a latent structure. The authors conclude that SDRBASED mice, particularly MISPCR, is a more suitable approach for automatic imputation model specification, especially when dealing with data generated with a latent structure. In the context of multiple imputation by chained equations, mice, this study explores the use of supervised dimensionality reduction, SDR, techniques to enhance the efficiency and accuracy of imputation models. The focus is on two SDR methods: supervised principal component regression, SPCR, and partial least squares regression, PLSR, which are applied in conjunction with mice to improve the imputation of missing data. The simulation study conducted in this research demonstrates that both SDRBASED methods can significantly reduce bias in the estimation of correlation coefficients between variables, particularly when the number of latent variables is large. This improvement is attributed to the ability of SDR to filter out irrelevant variables and concentrate on those that are most informative for the imputation task. The results also indicate that the performance of these methods depends on the number of principal components retained, with optimal performance achieved when retaining a small number of components. For MISPCR, retaining between 2 and 5 components is recommended, as this approach reduces bias and prevents algorithmic failures associated with larger numbers of components. In contrast, the optimal range for MIPCOVR is less clear, with the best performances observed when retaining the first components or a number of components just above the number of latent variables. The study highlights the importance of considering the relationship between the number of components retained and the supervision employed in these methods. In the case of MISPCR, the inverse constraint between the number of components and supervision can lead to the inclusion of weakly associated predictors when retaining a large number of components, thus limiting the advantage of using supervision in the PCA. For MIPCOVR, the fluctuating bias performance can be explained by the relationship between the number of components retained and the computation of alpha, which influences the proximity of MIPCOVR to MIPCR. This research also touches on the potential for adapting SDRBA-SED methods to handle non-normal data and categorical variables, suggesting the use of fit measures derived from simple logistic regression models for MISPCR and the development of specialized PLSR approaches for categorical outcomes. Further research in this area could provide valuable insights into the flexibility and applicability of these methods in various data scenarios. This paper explores the use of supervised dimensionality reduction for multiple imputation by chained equations, MICE, in the context of high-dimensional data. The authors propose a novel approach, named MISPCR, which combines the strengths of principal component regression, PCR, and partial least squares regression, PLSR, with the MICE framework. By incorporating a supervision element, MISPCR significantly improves the performance of MIPCR, particularly in scenarios where the data contains hundreds of variables. The paper discusses various PCA-based methods for dimensionality reduction, including traditional PCA, PCOVR, and PCA-MIX. These methods are designed to accommodate categorical variables and can be used in conjunction with MICE. However, the computational intensity of these procedures may limit their practical application, necessitating future research on computational shortcuts. The authors also highlight the importance of considering the potential limitations and assumptions of these methods, as well as identifying avenues for future work. They provide a comprehensive comparison of state-of-the-art methods for high-dimensional imputation, emphasizing the need for further exploration in this area. In addition to the theoretical discussions, the paper includes a simulation study comparing the performance of different imputation methods. The results indicate that MISPCR outperforms other approaches, especially in the presence of high-dimensional data. Furthermore, the authors provide interactive tools for visualizing and exploring the results of the simulation study, allowing readers to engage with the findings in a more dynamic manner. The paper concludes by emphasizing the potential of supervised dimensionality reduction for enhancing the efficiency and accuracy of MICE in high-dimensional settings. The authors suggest that the proposed MISPCR method could be a valuable tool for researchers dealing with complex data scenarios and encourage further exploration of its capabilities and limitations. The research paper discusses the application of multiple imputation, MI, in principal covariates regression, PCOVR, and principal components regression, PCR. It highlights the importance of understanding the relationship between MIPCOVR and MIPCR, particularly in terms of bias trends and precision recovery bias, PRB. The authors emphasize that PCR can be seen as a special case of PCOVR when the weighting parameter alpha equals 1. The simulation study demonstrates that as more principal components are retained in MIPCOVR, the bias in estimating the correlation between Z1 and Z2 decreases, and the PRB increases. However, for a certain number of components, MIPCOVR's performance converges to that of MIPCR. The paper concludes by emphasizing the significance of understanding the behavior of MIPCOVR and MIPCR, particularly in terms of their bias trends and PRB, to effectively apply these methods in real-world scenarios. Here is the combined summary of pages 27 and 28 of the research paper. The authors investigate the performance of multiple imputation by chained equations, MICE, with Bayesian linear regression, BLR, and Bayesian generalized linear regression, BGLR, under different mechanisms and proportions of missing data. Figure 5 displays the results of a simulation study, where the partially reported beta, PRB, is plotted against the number of complete cases, NC, for the correlation between Z1 and Z2. The data is generated under a missing at random, MAR, mechanism with a proportion of missingness PM equals 0.5. The figure compares the performance of MICE with MIPCR, predictive mean matching, and MIPCOVR, Bayesian linear regression, demonstrating that MIPCR outperforms MIPCOVR in terms of PRB, particularly when the number of complete cases is small. The authors also examine the impact of varying the number of imputations, L, on the performance of MICE. The results show that increasing L improves the accuracy of the imputed data, but at the cost of increased computational time. Specifically, the authors find that L equals 10 provides a good trade-off between accuracy and computational efficiency. Furthermore, the authors discuss the limitations of their approach, including the assumption of normality and the reliance on Bayesian models. They acknowledge that these assumptions may not always hold in practice and suggest that future work should focus on developing more robust and flexible imputation methods. Additionally, the authors highlight the need for further research on the optimal choice of L and the development of more efficient computational algorithms for mice.